Research in industrial psychology has demonstrated that human beings make predictable and costly errors in hiring decisions. In this video, I will explain a concept for a hiring analytics app that provides instruments that systematize the recruitment process and help hiring decision makers to avoid costly errors. A standard instrument that is used to avoid such errors is a scorecard, which is filled in by each evaluator in the hiring process. A set of criteria or qualifications are agreed upon by the hiring committee, and each candidate is rated on a scale of, say, 1 to 5 on each criterion. A rating is also given to the relative importance of each criterion, since for some positions one qualification will be of greater value to the organization than another. These importance ratings are used as weights. Each candidate receives from each evaluator a total score that is a sum of the ratings on each criterion, weighted by the importance of each criterion. The envisioned app includes a standard scorecard of this sort. The user need only enter the criteria relevant to the position and supply evaluator ratings of the candidate on each criterion, as well as importance ratings for each criterion. The app will then calculate subtotals for each criterion and a total score for the candidate. The standard scorecard is useful in hiring decisions where each candidate's capabilities are very well known, or in the initial screening of a large number of applicants where some guesswork at the candidate's capabilities is acceptable. However, in many contexts, the standard scorecard is insufficient. Suppose candidate A is known with certainty to be a little above average on one criterion, whereas candidate B could be very strong or very weak on the same criterion, and there is too little information to determine candidate B's ability. Should the evaluator guess at candidate B's rating? Or suppose one reference speaks highly of the candidate, but another reference who has worked with the candidate longer gives a somewhat lukewarm recommendation. Should the evaluator discount the first reference entirely and rely only on the second? It's unclear how to fill out the standard scorecard in such situations. The envisioned app therefore also includes a more sophisticated instrument, the Decision-Theoretic Scorecard, based on mathematical decision theory to be used instead of the standard scorecard for high-stakes hiring decisions. Instead of giving a simple rating on a scale of 1 to 5 on each criterion, the evaluator fills in a grid to represent the evaluator's information about the candidate on that criterion. The app makes this easy by allowing the user to click to fill in parts of the grid, and a default grid pattern is given so that the user need only modify the existing pattern. The grid has 5 columns, one for each rating 1 through 5. The user fills each column from the bottom up to the row that represents the user's estimate of the probability that the candidate should be given that rating. For example, if the evaluator considers there to be a 50% chance that the candidate is a 4 on technical skills, then the 4 column should be filled halfway up. The evaluator must then decide how to distribute the other 50% among the ratings 1, 2, 3, and 5. In all, 10 spaces in the grid must be filled in to reach 100% probability, and each column must be filled from the bottom. The app, in fact, will not allow filling from the top down. Once the grid is filled in, the app calculates the expected rating, that is, the sum of each possible rating of 1 through 5, weighted by the probabilities that the evaluator has assigned. In this example, 3.8 is the expected rating, the weighted average rating that the evaluator has given. This does not mean that we expect this particular candidate to perform at a 3.8 out of 5 in the area of technical skills. The candidate might perform much better or much worse than 3.8 out of 5. What the 3.8 out of 5 means is that if thousands of similar candidates were hired for similar roles, on average they would perform at a 3.8 out of 5, even though some of them would perform better and some would perform worse. 3.8 is the mathematical expectation, the weighted average performance. It is like an investment that has a few discrete possible returns, a 0% chance of a $1 million return, a 10% chance of a $2 million return, a 20% chance of a $3 million return, a 50% chance of a $4 million return, and a 20% chance of a $5 million return. The average return on such an investment is the mathematical expectation, that is, the weighted average, of these possible returns, $3.8 million. The investment might return $5 million, and it might return only $2 million, but on average, such an investment yields $3.8 million. The analogy with an investment is apt because a hire is a kind of investment. It cannot be predicted with certainty how successful a candidate will be if hired, so we have to look for the candidate who is the best bet, that is, the candidate whose average performance across the possible outcomes is highest. That is why the Decision-Theoretic Scorecard uses an expected rating that incorporates multiple possibilities rather than a single rating, which would essentially just be a guess at how the candidate will perform. So now return to the case where a candidate is known to be either quite strong or quite weak on management skills. The grid might be filled in this way, with a 40% chance that the candidate will perform at a 1 out of 5, a 40% chance of performing at 5 out of 5, and 10% each for 2 and 4 out of 5. This grid yields an expected rating of 3 out of 5. Now consider the example where one reference speaks highly of a candidate's organizational skills and another reference who has worked longer with the candidate is lukewarm. The grid should look something like this. Some chance is given to the possibility that the candidate will perform at a 4 out of 5 or a 5 out of 5. That is, we do not entirely discount the glowing recommendation from the first reference, but greater probability is given to the possibility that the candidate will perform at a 2 or 3 out of 5, since the lukewarm recommendation comes from someone who has worked with the candidate longer. This grid thereby takes into account all the information about the candidate. How do you as a user know exactly what probability to assign to each possible rating? The answer is that you don't, and you don't need to. What is important is not the exact probability that you assign, but rather the relationships between the probabilities assigned to the different ratings. If it is more likely that the candidate is a 2 than a 4, then the 2 column should be higher than the 4 column. If there's just as much reason to think the candidate will perform at a 1 out of 5 as that the candidate will perform at a 5 out of 5, then the 1 column should be just as high as the 5 column. As long as these relationships are represented, it does not matter much exactly which percentages are selected for each columns. There are, however, some guidelines that users should keep in mind, and I'll cover those in the next video. This video has explained the motivation for the envisioned app and covered the basic functioning of the standard and decision-theoretic scorecards. Watch the next video for tips on how to get the most out of the decision-theoretic scorecard.